Hello everyone, welcome back to the Console Multiphysics training course. In this lecture, we will be solving our first actual multiphysics problem, which is dedicated to the piezoelectric transducer. In order to start the modeling, we need to know what piezoelectric is and how we can do that in the software. Before we start the modeling, let's have some definition. Piezoelectric effect is the ability of certain materials to generate an electric charge in response to applied mechanical stress. In fact, when you apply a mechanical load, you get some electricity generated. Or if you apply an electric field, you will get mechanical stress. Some of the examples of piezoelectric materials are piezoelectric ceramics and piezoelectric polymers. You can find more information on internet. In piezoelectric materials, we have a direct effect, which is the generation of electricity when mechanical stress is applied, and this property is used in different applications such as sensors, accelerometers, energy harvesting, and so on. The other effect is known as the converse effect, which is the generation of stress or strain when the electric field is applied to the piezoelectric material. The application is for actuators, resonators, precision motors, and so on. Before we start our problem, we also need to know some more definitions. The first one is poling. Poling is basically orienting the dipoles of the piezoelectric material in a desired direction. It is done by applying a very strong electric field under certain temperature conditions. The other thing is the coupling constant of piezoelectric material, which relate the electric and mechanical behavior. In fact, there are matrices which show the relationship between the electric component and mechanical component of the piezoelectric material. Finally, the electrodes. Basically, in piezoelectric materials, electrodes are located in a desired place to collect all charges generated due to the mechanical load, or they are used to apply electric field for actuation. In this problem, we are going to model the direct effect of piezoelectricity in a simple case. As you can see in this picture, we have a piezoelectric layer which is clamped from one side, and a harmonic load is applied to the other side. The force is a sine function with amplitude of 1 and frequency of 4 Hz. We are going to find the electrical responses of the system after we apply such force. The top and bottom surfaces of the piezoelectric layer are covered by the electrode. In this picture, you only see the top surface. Right, let's go into the software and do the modeling over there. Okay, so as usual, we start with the model wizard, and here we are gonna have a 2D model. So we select 2D and wait to add the physics. Here we can add the piezoelectricity directly under structural mechanics. It is defined in the software. And if we select add, we can see that multiple physics are added here. So just wait for a few seconds and then we will see what is going on in here. So as you see, we have solid mechanics, which is related to the solid mechanics of our problem, and we have the electrostatics, which is actually the electrical part. We also have piezoelectric effect under multiphysics. That means we have a multiphysics problem. We can add them one by one separately, and then in the multiphysics add piezoelectric effect. But because we already have piezoelectricity in the library, we don't have to do that, right? That's it. Let's continue with the study. And here we have a time-dependent modeling because we want to see the time response of the system under the harmonic load. In some examples, frequency domain is also used for the piezoelectric modeling, especially when we deal with high frequency excitation. But here, let's work with the time dependent. So we select it and done. Okay, now we are in the software environment and we want to make our model. Before we make the geometry, I can show you that we have two physics added, the solid mechanics and electrostatics. Also have the multiphysics in here. In each physics, we have to identify the boundary conditions and the physics of the problem properly. Okay, let's start with the geometry and then make the rectangle that we have. So I added the rectangle, but before that, I want to change the unit to millimeter and then continue with the modeling. In here, we have a 10 millimeter width and 0.5 millimeter height. Then we can say build selected or build all objects because we have only one object, and form union, same as before, right? Now let's go to the material section and assign the material. In the material, we need the piezoelectric material. For this example, I'm gonna use PZT5H as a very well-known piezoelectric ceramic which is used in different applications such as energy harvesting. So if we open the material library and under piezoelectric, we can scroll down and find the PZT5H. As you see, we have many options. Another important and interesting case is the PVDF, which is a piezoelectric polymer, and you can use it in your modeling if you want. So let's continue with the PZT5H and then add two components. And after it's added, we can close the material library. Okay, because we have only one domain, the PZT5H is already assigned to that one, so we don't have to change or add any more materials. The next step is to add the boundary conditions related to the physics of the problem. If I click on Solid Mechanics, I will see that the domain 1, which is actually our system, has been already added here, right? We can also adjust the out-of-plane thickness, which is actually 5 millimeters, right? If you remember from the system. Now, because we have one boundary condition clamped and the other one under a load, we can simply assign it same as what we did in our previous problem. So let's see what we have here. We can have a fixed constraint which is applied to one end, and we can have a boundary load to the other end. So let's select boundary load. Okay, so the boundary load is applied to the other end and we have to define it properly. So I'm gonna use a total force, but here we need a function to apply the load into the system. We can directly write the function in here. For example, I can write 1 times sine, and because we have 4 hertz, 2 times pi times 4 times t as the force in here, and this is the force which is applied. It also says that the unit is not proper, but don't worry, it's not an error, it's just the unit. We already know that it's nil, and that's it. We are all set with the solid mechanics part of our design. Now we have to adjust the electrostatics part, which is actually the electrical boundary condition. In such problems, and especially when we have electrostatics, we need a ground boundary condition, which is actually the reference potential. So for this case, because we have one electrode in bottom and one electrode on top, we can select this one as the ground. I forgot to say that because we have a very thin layer of electrode placed on the piezoelectric layer, we do not actually need to model it as a material. In some modelings, we can also add it as a separate geometry as top and bottom electrodes, but in here we have a very thin film of electrode, so for simplicity we can just model it as a boundary condition. So one boundary condition is the ground, which is assigned to the bottom electrode, and the other one we can use floating potential, because electrode is a conductive material and we can use a floating potential to mimic a conductive material. So once again, because we have electrode assigned to the top surface, we can use a floating potential on the top surface, which mimics the conductive boundary condition. If I scroll down in the floating potential, we see that there is no charge or no voltage, which is correct because nothing has been applied to the piezoelectric before. Okay, don't forget to change the out-of-plane thickness of our system in the electrostatic physics. I think everything is set with our physics because we already defined the mechanical part and we defined the electrical part, and we don't have to touch the piezoelectric effect because it is already considered for our domain, right? So if I click on the piezoelectric effect, we will see that domain 1 is selected and coupled interfaces are solid mechanics and electrostatics. That's what we need. So you might be asking why we use electrostatics. The reason is piezoelectric material is a dielectric material without any conductivity, and we need to know the charge generation. That's what we need for a piezoelectric material, which we can do it in the electrostatic physics. Interesting. Let's continue. Before we continue, I want to show you something very interesting. As I discussed in my slides, we have the coupling constant or piezoelectric constant, and if you want to see them in our material properties, you can find them in coupling matrix. In fact, it's not a linear elastic material, it's a piezoelectric material, and the properties are defined in matrices. So we can expand these matrices and find the properties related to our material, but we don't need to know them for now. The interesting features of the console, which is the material libraries, and we can use the defined parameters over here. Interesting, right? So let's continue. The last part before solving is the mesh. For the meshing, again, we are going to use the software meshing feature. We are not defining it by ourselves, so we just use build all, and we have this mesh. I think it's a pretty large mesh. I want to use the extra fine to make our simulation even better, and that's everything with the meshing. And as you can see, we have much smaller meshes. The last step is the study. In this case, we can have a time range to solve our problem. I want to select 2 seconds. As you see, the range changes from 0 to 1 second. As the default setup of the software, I will change it to 2 seconds. And I want to make the time interval even smaller to have more precise solution. I think that's it for now, and we can now press compute. And we need to wait to solve the problem. Okay, the problem is solved. Today I want to discuss the results a bit more, and you will see how we can get more information about the problem which is solved. As you may remember from the previous video, I told you that the software can create some default results based on the physics of the problem. From the solid mechanics, we have the stress results, and from the electrostatics, we have the electric potential generated in the piezo. Let's look at them more carefully. For the stress, and as you see, we have the results at the final time step. We can play with this time step and get the shape of the structure, but this is actually the exaggerated shape, not the actual deformation, and it shows the stress developed through the structure. As we expected, the clamp side has the maximum stress on the top and bottom surfaces, if you know the mechanical engineering part. At 0 seconds, there is no stress, and as we have time increased, for example at 0.28 second, we have the stress and the direction is upward. It is based on the load that we applied. If we give another time, we have another direction. Remember, we had a harmonic load applied to the system, so the system goes up and down. This is actually the von Mises stress generated in the structure. You may know what von Mises stress is in a solid mechanics system. If we also try another time, for example 1.22 seconds, you may get another result. The same direction but different stress. We can also have another time, and eventually we have the last time, which is 2 seconds. Okay, it's very interesting. We can also get the displacement if we want, but let's go to the electric potential. We can also get the electric potential generated through the system, again at different times. For example, at 1 second, we can see what the electric potential is, and we can get for the other times. So that's easy. But as you see, such information, which are actually the 2D surface information, cannot give us a more understandable result for us in terms of the output of the piezoelectricity. As you remember, we had one electrode in the bottom surface and we had another electrode on the top. So we want to see what is actually the generated potential on the top electrode. So in fact, we want to see the output of the system which is generated on the top electrode. As you remember from the definitions, the electrodes are meant to be used for collecting the electricity generated. In future examples, we may show you how we can get this output into an electric circuit. But for now, let's see how we can find the electric potential generated in the top electrode. In the bottom electrode, we won't expect any electric potential because it is grounded, right? And on top, we have the electric potential generated on the electrode, right? Because we need a number, we can go to the derived values, right click, and because we have a conductive boundary condition on top, we can use the line average. The line average gives us the average of any feature that we are looking for in here. We select this boundary, which is our top electrode, and then in the expression, if we expand it and then we go to the electrostatics. Under electric, we can find electric potential. We can have further more properties and outputs if we want. We can find electric field, polarization, electric field norm, and if we go to current and charge, we can deal with the surface charge density. But for this problem, let's click on electric potential. So we have added here. We can also add more expressions, but for now we need the electric potential generated on the top electrode, and we use the line average. I think that's it, right? Let's click on evaluate and wait a few seconds. If we do so, we have a table added here. For different times, we get the electric potential. This table is also created here. So if we want to delete it or delete some columns, we can do it either here or we can remove it from here. As you see in table 1, we have time as the first column and electric potential as the second column. This actually shows the average electric potential on top electrode, which is what we are looking for, right? So let's plot it. In order to plot this, we have to go to results, right click, and we need a 1D plot group. Even if you don't know what option you need to select, you can see that it shows us a curve. So let's click on it. And after we click on that, we can again right click on it and use table graph, right? This is table graph created in here. The interesting part of COMSOL is whatever you don't know, but because it has some sort of similarity with other menus, you can try on and find that. For example, right clicking and adding is something that we have done so many times in our simulations. So in the table graph, table 1 is already added because we have only one table. In case we have multiple tables, we can select it from this drop down menu. So we don't have to touch anything else. The X data is automatic. We can also use time S, which is already the X axis, right? And I think that's it. We can click on plot, and there you go. Very interesting results that we were looking for. It shows the time response of the electric potential generated on the top electrode, and as expected, it's a harmonic function because the load is harmonic. So I think that's very interesting. It gives us very useful information about the phase and the amplitude and the shape of output signal. It can be used in many other purposes like energy generation or sensing applications. In many other cases, we can look at the simulation vice versa. We can apply an electric field or electric potential and then get the mechanical output, which is actually the converse effect. But for here, we model the direct effect, which is basically the output electric potential under a harmonic mechanical load. I think that's a very interesting result, and it's enough for today. We can also export this result as we showed before. If you want to export the graph, you can right click and use image or plot. Now click the plot and export. When we select plot, in here we have to select what plot we want to select, and in here we use 1D plot group, which is actually in here. We can rename it here. For example, we can use output voltage, and then when we want to export, we can select output voltage, which is easier for us to find it. And we can also browse and assign the folder to export it, and it gives us the spreadsheet, which is actually the points. If I assign it and then export, and then I open the spreadsheet, I can see the time and voltage values. So I just opened it, and there you go. We have some information about the file. For example, when we created it and what are the dimensions and the nodes. We have the time in the first column, and we have the output voltage in another column. These are the actual raw data, and we can use it for many other purposes. We can use that in other software like MATLAB. We can plot it, we can apply filters, we can use fast Fourier transformation for that, and many other signal processing functions. Very interesting, right? So in fact, we have done our simulation, we got our output, and we exported it in a desired shape. Last but not least, don't forget to save your model, otherwise you're gonna lose it. The saving is pretty much same as other software. just click on save and assign the folder for that. Okay, thank you very much and stay tuned for the next videos.